Good morning, everyone. Thank you for coming to our seminar. It's my great pleasure to introduce Dr. Nicholas Harmon, hosting here in our UTIG Friday seminar. Nick, can I call you Nick?
Sure.
Okay. Nick is a marine geophysicist and seismologist working primarily on mantle flow dynamics in different numerical methods and the interaction of tectonic settings between the mantle and the rigid lithosphere. Nick started his academic journey as a bachelor at Boston University. From there, he moved to Brown University, where he did his master and PhD, where he graduated in 2007, had moved to Scripps for a postdoc as part of the REACH program, working on geodynamics and seismic modeling for imaging a mantle plume and seismic anisotropy. Then he moved in 2009 to Southampton, taking the position of lecturer, where I kindly met him when I started my PhD. He was a chair at my PhD panel committee. And I was lucky enough, he took me to see to this experiment within 2016 on the deployment cruise. And since then, he was until in Southampton until last year as an associate professor when he moved to Woods Hole, taking a research specialist position. Some of the areas that Nick works on, and notice the fun places, Papua New Guinea, Afar, Hawaii, the Lesser Antilles, and this study that you going to see some of joint results from Seismic and EM. So, welcome.
Thanks, Eric. That was a lovely introduction. So yeah, today I'm going to present a lot of work from the PyLab experiment in the Equatorial Mid-Atlantic Ridge. And what I hope to do today is kind of maybe change your view of the Oceanic Lithosphere-Asthenosphere system, and then hopefully encourage you to think a little bit more broadly about how the oceanic lithosphere and the continental lithosphere may evolve and change through time, and kind of get rid of kind of this nice smooth perspective. Torsten was here. Get rid of this nice smooth perspective, you know, everything's half-space cooling, et cetera. It's a bit more dynamic than we think it is, and a lot more exciting, I think. And I'm just going to take a moment to thank my many collaborators, particularly Kate Reichert, who is also my partner in getting this project off the ground. The dolphins are there to remind me that when I went to sea, it was like a complete dead zone. When my wife went to sea to recover the equipment, there's dolphins jumping over the bow of the ship. So, you know, I'm just saying. Anyway, sense of humor there. All right, so the classic definition of the tectonic plate is that it's a rigid, strong plate that moves coherently over a weaker asthenosphere beneath it. And typically, when we think about temperature profiles, the physics of what's going on there, we think of the lithosphere as being the conductively cooling part of the system, which has a pretty strong geothermal gradient associated with it. And then the convecting mantle is well mixed, has a relatively homogeneous temperature. And we think that the lithosphere-asthenosphere boundary is where, at least in a thermal sense, where this steep geothermal gradient intersects that adiabat. And this is probably what you learn in textbooks. But why is the lithosphere-asthenosphere boundary important for our understanding of how plate tectonics works? Well, for a variety of reasons. Number one, it's the largest plate boundary aside from the free surface, if you think about it. And it's very important for understanding mantle dynamics. So how does the mantle convect? Is it layered convection? Is it whole mantle convection? Is there small scale convection? Billions of years ago, when the continents formed, continental lithosphere didn't exist. So the continental lithosphere in some way has to be derived from oceanic lithosphere. So if we can understand how it's produced and evolving today, it gives us insight into, you know, billions of years of Earth history. It's also important for the driving forces of plate tectonics. How that plate moves over that weaker asthenosphere is part of the resisting forces in the plate tectonic force balance. And so how much of that resistance is going in, how much of the slab pull, ridge push, et cetera, are driving the system. And then finally, plate tectonics is really important for our understanding of natural hazards. So most earthquakes happen at plate boundaries, volcanoes happen at plate boundaries. So understanding the whole system kind of hinges on understanding the lithosphere-asthenosphere boundary system. And then finally, this climate thing here, if you think about how we understand sea level in the paleo land, you know, for hundreds of millions of years going back in the geologic record, if you want to understand that, you have to understand how the freeboard of the continents relative to the oceans occurs. And to do that, you need to understand the lithosphere-asthenosphere system. Okay, so this is kind of a simplistic view of the oceanic lithosphere. So this is a seismic model from, if you can pick your favorite global seismic model, we picked the Berkeley Group's one here. And if you just take an average of seafloor age of the entire model, you see kind of what you expect from half-space cooling. You see a thickening lithosphere, you see a low velocity asthenosphere beneath it. So the blue stuff is the lithosphere, the red stuff is the asthenosphere. And it's relatively smooth and kind of looks like what you would expect for half-space cooling. And then on the right-hand side here, what I'm showing you are predictions from a particular model for converting olivine into seismic velocity. So this is shear velocity based on some attenuation relationships from Jackson and Powell. And that moved without being expected. Okay, hopefully I didn't record any timings. Okay, back. And so what you see from this, because this is primarily based on temperature, these velocity profiles are relatively smooth, right? And that's pretty much what you're seeing in this global model. So this is great if your worldview is predicated primarily on surface wave models. Half-space cooling is brilliant, looks wonderful, totally believe it, solves all the problems. We don't need to go to the ocean lithosphere anymore. We don't need to study it because we know it, right? Where's Torsten when I need him? Okay, anyway. So there's a few hiccups in this. As we've gotten better at making observations in the oceans in the past 20 years or so, I think the MELT experiment is like the first kind of big broadband ocean bottom seismic deployment, and we've been doing a better job since then. So if you look at what's plotted here are individual estimates for the lithosphere-asthenosphere boundary from scattered waves. So scattered waves are P waves that hit a velocity discontinuity and convert to an S wave, or an S wave that hits a velocity discontinuity and converts to a P wave. And we can use that information to kind of pick out where we think the base of the lithosphere might be. And so this is just a compilation from a variety of different studies using a variety of different scattered phases. And what we see is, okay, well, this is viscosity up here, this is temperature down here as a function of age and depth. And basically, it kind of falls along a temperature contour, which is, okay, that's great. So the lithosphere-asthenosphere boundary is defined by temperature. But there's a problem with this, because scattered phases only exist if there's a sharp velocity discontinuity. So several percent velocity change over a relatively narrow depth range, so less than 10 kilometers, let's say. And so if you look at these profiles over here, well, you have a velocity change that's occurring over almost 100 kilometers, and you would never get a scattered phase from a velocity profile that looked like that, right? And instead, you need something rather sharp. So what the scattered waves are telling us is, well, actually, in a lot of places, this lithosphere-asthenosphere boundary is really sharp. And you can't really do that with temperature, because temperature diffuses relatively rapidly. You know, within 10 million years, any sharp temperature gradient diffuses to something that's not sharp. Okay, so this is telling us that something other than temperature is required to explain the lithosphere-asthenosphere system. I'm going to say MELT about 1 million times. If this were like a drinking game or something like that, you would probably have trouble walking out of the room at the end of this. But we know that MELT exists in the mantle. It has to exist because we have things like volcanoes, mid-ocean ridges, et cetera. And in a lot of places where we've gone to mid-ocean ridges, for example, both seismic studies, so this is the cartoon from the MELT experiment. So and what this reddish stuff here is showing you is the MELT triangle beneath the mid-ocean ridge. And it actually extends quite a ways away from the mid-ocean ridge here. It's quite broad. On the other hand, magnetotellurics is also really sensitive to things like partial melt. And typically they image partial melt regions as regions of very conductive material or low resistivity And this is an example a little bit further north on the East Pacific Rise. So this is from the EPR at 17 South. This is from 9 North. And what you see here is, again, so they've put a nice line for the dry solidus, the wet solidus, and it seems they have a resistivity anomaly directly beneath the ridge. It's probably associated with melt. Notice how the resistive lid, which you'd associate with a lithosphere, is actually thickening really quite rapidly in this study. It's quite amazing, right? If you look at the scale from 100 kilometers away, it's going from maybe 20 kilometers all the way up to 100 kilometers. People don't often think about that, but so that's telling you something is happening very, is changing very rapidly there. Probably a little bit different than what you'd expect from half-space cooling. Okay, so the scattered wave imaging and a lot of other studies have reported melt. Presents a bit of a problem with the worldview that everything is defined thermally. So people have tried to come up with alternative explanations for melt in the asthenosphere. On one hand, people say, well, actually, maybe it's not a, it's not a real boundary in the sense that maybe you're just misinterpreting your seismic data, and actually what you're seeing with the scattered waves is an anisotropic effect. And if you want to make a seismologist cry, you start talking about anisotropy or attenuation, because both of those things are hard to model and difficult to deal with. So this, and there have been quite a number of studies. Some of your colleagues have even been on some of them that have argued that, well, maybe anisotropy is what's causing these scattered phases, and actually the lithosphere-asthenosphere boundary is just one of this. Okay, that's fine, but it doesn't always work. And, I think the jury might still be out on this, because anisotropy in general is very difficult, and we can have a much lengthier discussion about that later on. And then there's another camp of people who say, well, actually, maybe it's just missing physics and our understanding of how things work. So it's a real effect that you're observing. Something is changing and causing those scattered phases, but maybe it's not melt, maybe it's something else. So people have proposed that maybe it's the oxidation state of the mantle, which is probably only really important in subduction zones. So when you're looking at mid-ocean ridges, this one's not so useful. There's elastically accommodated grain boundary sliding, which is basically an enhanced attenuation effect. And what attenuation does is it trades off with velocity. So you can have higher attenuation, which would make things slower. But if you're not accounting for that attenuation, it looks like you have a sharp change when it's actually just a change in the activation of this elastically accommodated grain boundary sliding mechanism. There's not a lot of laboratory data that supports this hypothesis. So again, the jury's still out on that one. And then other people have argued, well, actually, if you have olivine that's really close to its melting temperature, maybe its velocity will be lower due to lots of kind of microstructural effects that aren't being taken into account. And again, all of these ideas are interesting and plausible and may actually be happening in the Earth, but none of them is as satisfying as just saying there's partial melt in the asthenosphere, and that's helping to define the lithosphere-asthenosphere boundary. So there have been lots of different hypotheses about how melt might exist in the asthenosphere, and there are different observations that kind of support different ideas about melt in the asthenosphere. So some people have proposed that partial melt may kind of coalesce at the base of a chilled lithosphere, and that may guide itself to the mid-ocean ridge. And then there's been some active source seismic observations in the Atlantic that also kind of support the idea that there may be channels of melt at the base of the lithosphere. Some people have argued that you may have both things going. So you may have a mid-ocean ridge melt triangle, you may have permeability on a melt boundary, and then there may be some frozen in melt later on, and maybe that's what's helping to cause the scattered phases. And then other people have argued, well, maybe you don't need that much melt, maybe it's just the particular melt geometry that helps cause the scattered phases. But as I mentioned earlier, there are lots of observations that are consistent with melt. And then at the mid-ocean ridge in particular, how does this melt triangle actually look, and how does it behave? Because this is one image that's very different from a very similar spreading system, right? So seismology and magnetotellurics are telling us different things. But the other big problem with this is, all the ideas from these different studies are coming from different areas on Earth, right? So 17 South versus 9 North. And there hasn't really been a complementary set of observations in a single place where you could actually try and tease out, well, okay, are my observations an artifact of my ability to resolve things, or are they real, or what's going on? And the idea, well, try one more time, there we go. And the idea behind the PyLab experiment was to make a comprehensive suite of geophysical measurements in the same place with a wide variety of resolutions and sensitivities to try and tease out what's actually going on at the Lithosphere-Asthenosphere boundary. And so this experiment, in addition to deploying, so each of these little circles here is one of our stations, and we had a broadband ocean bottom seismometer and an ocean bottom MT sensor. And so the data recovery in general was pretty good. The little X's show where we weren't able to recover any data from a particular station. Red is either MT, black is seismic. But in general, the data recovery was quite good for this experiment. And then just to orient you a little bit, you'll hear me talk about this northern line, which is north of the chain fracture zone, which is located here. This is the Romanche fracture zone. Africa's up there. And then line 2 is south of the chain fracture zone. So I'll be showing a lot of different profiles from those two particular areas. The other thing that we did was we collected marine geophysics, so gravity, magnetics, and swath bathymetry. And then our colleagues, Ingo Grevemeyer and Satish Singh, collected several rounds of active source data, which is, they published over the previous several years in various highfalutin journals that complemented the work in this area.
Can you just say a minute about what you showed the Equatorial fracture zone area for this? That wouldn't be the first choice.
Everyone says that.
Well,
that's right. Well, no. So this is one of these quandaries that you always have. Where is the ideal place? So you could go further north where you have relatively short ridge segments, and it's a relatively straighter. One argument that we have for doing this particular area is that within a relatively compact region, because of the Romanche offset there, we can go out to 80 million years. So we're covering a huge range of seafloor in a relatively compact thing. The other side on that is that this was partially determined by where Satish could get ship time from Western GECO. So they had a ship going out of Africa and they were going to go through here. So we had to organize a little bit. But yeah. Okay. Good question, huh? Comes up a lot. Okay, so now I'm just going to take you through a lighthearted romp of the findings of the experiment. And what I'll try to do is build up and integrate our understanding of what's going on in the subsurface with each new data set that we were able to get information from. So I'll start with surface waves. I'm a surface wave guy. I can't help myself. So this is just showing you kind of the ray path coverage that we have for the teleseismic earthquake study that we did. So this is using Rayleigh waves, so the vertical component. And then we also had ambient noise, cross-correlation information to add into the inversion. So generally pretty good data coverage. Okay, so in the top two panels, we're looking at depth slices, so at 26 kilometers and 78 kilometers. The ridge is shown here as this white line. Two profile lines, 1 and 2 are shown in dashed lines. And then down below, we have profile 1 and profile 2. So at 26 kilometers depth, which is roughly in the lithosphere, we see what we might expect to see. We see low velocities centered on the mid-ocean ridges, and the velocities are increasing away. And then as we go to 78 kilometers depth, we see that it's not really a very homogeneous. So this would be comfortably in the asthenosphere. It's not really, it's not a homogeneous asthenosphere, right? There's quite a bit of low velocity anomalies, so 4.1 in several places, and not necessarily directly beneath the ridge axis. In fact, the anomalies associated with the ridge axis are offset to the west, and there are several off-axis low velocity anomalies. Looking at it in profile view, we can see that there's a lithosphere, and there's actually a pretty thick lithosphere directly beneath the mid-ocean ridge. To a lot of people, this is surprising. If you're like a fan of like the late 80s, early 90s kind of mid-ocean ridge stuff, this is kind of expected because lateral conductive cooling will tend to give you, at slow spreading rates, will tend to give you a thicker lithosphere beneath the mid-ocean ridge. And this has, we'll see later on, actually has pretty important implications for melt transport and things like that. But then you also see a lithosphere that thickens pretty rapidly and is more or less thickening with age. You know, it's not a perfect, but in general, it's thickening. And then in the asthenosphere, we see these punctuated anomalies that we saw in the upper right-hand corner at 78 kilometers. We see several of those off axes in the asthenosphere. But then we also see some interesting things. So here we have a very high velocity feature, which looks like a drip, right? So already what we're seeing in the asthenosphere is a relatively complicated picture, maybe a dynamic picture of things that might be rising and falling directly beneath the lithosphere. There you go. Okay. So surface waves, as much as I love them, have their limitations. They're not good at getting discontinuity structure. They tend to smooth everything out because what they're really sensitive to are depth averages of velocities. And within those depth averages, you can have very, very different structures. And we'll see that a little bit later on in the talk. Receiver functions, on the other hand, are very good at getting velocity increases or decreases with depth. And we're going to talk about two different methods here. One is an S to P converted phase. So an S wave comes up to a boundary, gets converted to a P wave. And then the other one we're going to look at is a P wave that comes up to discontinuity and gets converted to an S wave. And we can use that source P wavelet or S wavelet and deconvolve that from another component of the seismogram to generate the impulse response of the Earth. So where the change in velocity discontinuities happen in the time domain. And that's what this diagram on the side here. So these little blips are telling you where one of those velocity discontinuities occurred. And so just to help orient you when we're looking at these plots, red is a velocity increase with depth and blue is a velocity decrease with depth. Okay, so kind of starting shallow and working our way down. So the S to P receiver functions are kind of like a blunt instrument, kind of like James Bond. You know, they tend to be lower frequency because S waves in teleseismic data are low frequency. But in this case, we were actually able to image variations in the MOHO going across the region. And we image a MOHO that's roughly 4 to 8 kilometers thick, and there's some variation. And if you look at it sideways and squint, you might convince yourself that, you know, we have relatively thin crust over here, which kind of lines up with thin crust over there. And relatively thicker crust away from the chain fracture zone. And then up here, what we've done is just plotted stacks of these, and you know they're reasonably well resolved. The gray area is the error bar, so they're above 0, so we can say they are interpretable. And then working our way down, what we were interested was the lithosphere-asthenosphere system. So the red stuff here is the MOHO, which is velocity increase from the oceanic crust to the mantle peridotite beneath. And then we see this blue phase, which is a velocity decrease, where we go from the lithosphere down into the asthenosphere. This is quite pleasing as a seismologist because these are independent data sets. They don't necessarily have to agree, but the LAB phase is lining up quite nicely with the steep gradient and the surface wave velocity contours. And in particular above this low velocity zone. So there's a pretty sharp gradient here that you would pick out from the surface waves. And what we see is a 20 kilometer, approximately 20 to 30 kilometer thick lithosphere beneath the mid-ocean ridge, increasing down to about 50 and maybe even greater further away. On the other side, notice that it's a bit patchy. On the other side, we see another blue phase, which again pops up where we have a strong velocity contrast or a steeper velocity contrast going all the way down to 4.1 kilometers per second. And so if you kind of take these blue phases where you see them and plot them up on a map, you see a general trend where you have thinner lithosphere near the mid-ocean ridge. And in general, it works pretty well on the west side. It gets a bit more complicated on the eastern side there. And I'll show you for full disclosure. So this is the southern line. This is the northern line. and it's a lot more complicated. So we see energy coming in. There's maybe evidence for a double discontinuity here. It seems to be undulating, so it's a little bit more complicated. This is like if you want to feel okay about half-space cooling, this is the soothing one, you know, the increasing depth away from the ocean ridge. So what this is telling us is, okay, well, maybe the patchiness of it is telling us, well, maybe there isn't melt everywhere in the asthenosphere in this particular location, right? If the presence or absence of the LAB phase is determined by the presence of partial melt, then this is kind of giving us some indication of where there's a significant amount of melt built up. Okay, we can use receiver functions to look even deeper. So we had a very talented group of people working with us. So we were able to image the mantle transition zone. So typically mid-ocean ridges aren't really considered to be particularly significant for whole mantle flow, kind of the Louise Kellogg type diagrams and things like that. The mid-ocean ridge is doing whatever it wants, and there's two layers of convection. It's mostly drawing material from the asthenosphere and never really pulling anything from through the 410, 660. And I'll focus mostly on the transition zone thickness because that's relatively easy to convince people. But what we actually observed was a fair amount of thinning of the transition zone. And thinning is typically associated with hot upwellings like mantle plumes like Hawaii and things like that. But we actually observed that at the mid-Atlantic ridge. And we said, okay, well, we have our study area, maybe it's not representative of the entire mid-Atlantic ridge. Let's go look at velocities across the entire mid-Atlantic ridge. And so we picked our favorite model and looked at it. And you can see that, there's typically low velocities directly in the transition zone, directly beneath the ridge. So this kind of suggested to us, well, maybe in the mid-Atlantic, the mid-ocean ridge, and this is a chicken or egg thing, either there's mantle flow coming from deep through the transition zone and helping to drive the mid-Atlantic ridge system, or the mid-Atlantic ridge system is actually strong enough to pull things from deeper. And there are arguments for or against, and that's just what this diagram is saying over here, is that the mid-ocean ridge system is actually interacting with the deep mantle and actually suggesting that there is whole mantle convection beneath ridges. Okay, so that was kind of something we didn't expect to get, but we learned a lot from. Okay, so we've done surface waves, receiver functions. We also had magnetotelluric observations. And Shengguo Wang did a really nice job dealing with some technical difficulties given the ocean basin that we were working in. And he produced these two images. So this is the northern line and the southern line beneath chain. And what you get are actually two very different looking pictures. When we first plotted this up, we thought we made a mistake. If you're sitting in the back of the room, you might say, oh yeah, Nick, that looks kind of like the surface wave model you just showed us. Are you sure you got the right data plotted there? No, this is the resistivity model. So these low resistivity anomalies are almost spot on where we see a lot of these low shear velocity anomalies. And in addition, we also see relatively high resistivities in the mantle where that drip is, which we were quite chuffed about. The southern line, on the other hand, is a bit more complex and looks a lot less like our surface wave model. And in fact, there's some interesting features in here, what's plotted here. So this is the LAB from receiver functions. What you see here is there's actually a low resistivity channel beneath the lithosphere. So this blue stuff, the high resistivity stuff would be considered the lithosphere. And there's a channel underneath it. And this is similar to what others have seen seismically, that there may be these melt channels at the base of the lithosphere in different parts of the mid-Atlantic ridge system near us. The problem is this is kind of a classic example of differences in sensitivity between methods giving you conflicting information, right? So a lot of people look at this and say, well, those don't look anything like each other, so those channels must be bogus, or your low velocity anomalies must be bogus. And then you may also ask yourself, well, if you have a melt channel, why don't you have really sharp velocity discontinuities that you could image by receiver functions, right? It's a good question. And we can go through and look at these individual profile. So the surface waves are kind of these smooth things, and then in the red and gray or blue lines are models that fit the receiver function data, showing you, simplistic, this is the kind of velocity contrast and the depth that you need to explain the receiver functions in different panels. If you step back, horseshoes and hand grenades, the surface wave model and the resistivity models are similar, not precisely spot on all the time. The receiver function models also kind of suggest lithosphere-asthenosphere boundaries that are kind of in the same depth range as the surface wave anomaly, which we already kind of knew just by looking at it. But the resistivity model with these channels, so these little notches here, aren't really represented in the receiver functions. But there's an explanation for that. So S2P in general is a low frequency phase. So its ability to resolve a thin channel. So this is just showing you, we had a thin channel, we made a model with a thin channel, and then we looked at using S2P for different frequency contents. And we're around this 0.15, 0.1 hertz kind of high end of the bandpass. And you can see that this black line has no evidence for a positive negative value, whereas you can see some of these have this positive negative phase that comes through, right? So basically, if we have something that's on the order of 10 kilometers, which is what they have in the MT, we wouldn't resolve it. We'd just resolve a negative associated with it. And then you may also ask the question, well, is MT just giving out some spurious anomaly channel because it just felt like it? And so we did some resolution tests. So if you have an input that looks like this, you'll get an output that looks like that, which looks reasonably close to what you put in. And the same thing with the channels. Even if you have low resistivity anomalies deeper down with a channel above it, you can still pull out a channel and you have some indication, but they're quite smeared out. So we're pretty confident that the channel structures are robust, especially given that Satish has published several papers that also seem to see it, right? So they're there. Well, I shouldn't have to convince you guys, but you're with me, right? So, we can kind of, if you plot all these things together, you can pick at it and say, okay, well, it's not a perfect match, but we're starting to get to the point where we think we know what's going on. So we can improve our models further, though. So as I said earlier, surface waves are kind of flexible in the sense that they're really just sensitive to averages over depth ranges. So there's a wide variety of structures. And if you've ever read any papers where they do surface wave inversion with Bayesian type analyses, you always see giant error bars on it. And that's because there's a lot of things that can satisfy surface wave dispersion. So we wanted to explore whether or not we could come up with a structurally similar surface wave model that satisfied the dispersion data just as well as our smoother model did, and be more structurally similar to the resistivity model. And so the first thing we wanted to do is understand, well, is there a relationship between resistivity and shear velocity structure given some, simple assumptions like a half-space cooling model? What does that look like? So we calculated the thermal profile for a half-space cooling model. You can calculate what you think the melt triangle might look like in a half-space cooling model, making some assumptions. And it approximately covers that area. We can convert this temperature profile to shear velocity using different parameterizations. We chose a particular one, and you get a map that looks like this. And then you can also calculate what you think the resistivity should be based on an olivine mantle, and you get an image that looks like this. So without melt, if you just take this map and plot it up as a cross plot, you get these black dots, which seems to define a trend that you can fit a line to. And that's pretty much what we did. We said, okay, well, I can put a line in the middle of those dots, and that line gives us kind of a low grade relationship between them without having to do much work. So the simplest parameterization that we could do. The other interesting thing is if you say, okay, well, that's my melt triangle, those temperature and pressure conditions, and you put 0.1% melt in there. And because resistivity is sensitive to interconnected melt, and it's also sensitive to volatile content in the melt. If you add more water to the melt, and this is a lot of water, 4% up to 20%, you get big changes in the resistivity relative to the shear velocity. And so just looking at this, simply put, you could potentially map where you think melt is using shear velocity and resistivity together. So that's helpful. But you can actually go one step further and you can start to map the volatile content of the melt, which is even cooler. So now the geochemists should all perk up and get excited, because now you can understand a lot more about what's going on in the system. Okay, so we did the same exercise for the resistivity and shear velocity model from the surface waves. So that line that I showed you earlier is plotted through here. And then the colored background is just kind of like the 2D histogram of the data plot. And depending on your field, you might look at that and say, hell yeah, that looks like a great relationship. And other people might say, well, there's a bit more improvement to be had. But the correlation coefficients for the two different profiles are 0.43 and 0.39, which probably isn't significant by most tests, but it's not zero and it's not totally uncorrelated. So, geophysics, pretty good, right? And the other pleasing thing about this is that simple petrophysical prediction that we had actually goes right through the middle of those fields, right? So we're actually doing quite good with just a very simple model. So then we said to ourselves, okay, well, if we just take this simple line and convert the resistivity model to a shear velocity model and use that to seed our shear velocity inversion, what parts of that synthetic shear velocity model does it keep and is it happy with? And can we fit our data just as well with some of those features? So what I've shown here is just we've taken that line and converted the MT model to VS. And then we use this as our starting model for the shear velocity inversion. And the result is shown down here. And amazingly, it keeps a lot of the structures, these two anomalies are better centered on each other. And some of the shallow anomalies in the shear velocity inversion maybe pop out a bit more. The drip stays, which was there a priori anyways, so that's good. But this is probably the cooler profile, right? So the surface waves are totally happy to have a low velocity channel at the base of the lithosphere, right? And they kept this feature. It makes some modifications and things trade off a little bit, but for the most part, you can construct a structurally similar model between the MT and the surface wave velocities and get, and convince yourself, well, actually these channel features are robust because they're not, if they caused a worse fit in the data for the shear velocity inversion, then you shouldn't keep it, right? It's not a robust feature that the surface waves need. So if we take our final model from that inversion, which fits just as well as our previous iteration of the model, and make a cross plot, our correlation coefficient goes up to 0.6, which is kind of starting to get into the more meaningful realm of relationship. But then the other really nice thing is that if we plot, again, we plot those fields from the half-space cooling model on top of our data, a lot of our data can be explained with that simple model. And now we can play some fun games, right? So this is just showing you visually what happens when you change the melt percentage and the amount of water in the melt and where those fields move. And so now we can take that information and search over what combinations of melt fraction and water content satisfy each individual shear velocity and resistivity anomaly. And that's what we did. And what we found is, we get up to 4% melt. The water content in general is under 10 weight%, which is a little bit higher than what the geochemistry coming out at the ridge is. We can also map that into CO2, but again, we get relatively high values of CO2. We can also add sulfide melt to it, but again, it's a little bit higher than what's needed from the geochemistry coming out at the ridge. And you could have combinations of these things. Or you could argue, well, maybe there is super wet stuff down there, but it's just not coming out at the ridge. So there's like a sampling bias, or, there's more work to be done. And, I'm agnostic on a lot of this thing. I think the value of this work is just showing that if you have consistent data sets, you can make these analysis and laboratory things and modeling have to catch up. Okay, so I'll show you the body wave model for completeness in terms of tomography. And what's plotted here underneath are the P-wave and S-wave anomalies for the north and south line. But again, the interesting take-home thing is that we actually, in the body wave tomography from local earthquakes, we actually see a channel. We see evidence for a channel. So again, that's another piece of independent information that's telling us that some of these features are real. Okay, and then should I stop at 45 minutes or?
As long as you need.
As long as I
We've got another 15 minutes, so.
Another 15 minutes, okay. Well, don't say that, it's like all right, there's another piece of information that we have is anisotropy. Anisotropy, typically in oceanic settings, we typically think of it as reflecting information related to the alignment of olivine due to shearing by plate stresses. And again, for the most part, these blue SKS splitting measurements, which are shown on top, kind of point in the direction of plate motion, which is what you would kind of expect. But then there are these giant red ones, which are close to 3 second splitting time, and they're ridge parallel. And it's really hard to explain those splitting measurements with olivine fabrics. So you need something more exotic. One way to do that is to have vertically aligned melt in the lithosphere, because that can and does produce, modeling is shown, it can and does produce strong splitting that would be, so as long as the vertically aligned melt is kind of oriented in the ridge parallel direction, you would predict to get very strong ridge parallel splitting. And then this is just to compare and contrast what the picture looks like in the Atlantic versus the Pacific. So the Pacific, this is from 17 south at the EPR, really does look like half space cooling. There's no lithosphere directly beneath the ridge. The ridge is here. The asthenosphere looks like it goes up to the base of the crust. And then you have very gradual thickening of the lithospheric mantle. Whereas here, we have very steep walls on the development of the lithosphere and relatively focused melt underneath it. So our argument for this is that it's likely the lithospheric structure that exists in the Atlantic that's helping to focus, melt into cracks to feed the volcanic system. Okay, so just sum up a little bit, and I'll try and get through the rest in about 5 minutes, so there's time for questions. Okay. So again, just to sum up, we have these punctuated anomalies in some cases, which look like they might be upwelling melt, and then we have a downwelling drip, which is kind of consistent with small scale convection. But then sometimes we also see melt in channels beneath the Lithosphere-Asthenosphere boundary. And so in the same location, we actually have two melt geometries which have been proposed in other places, which is kind of interesting because that suggests that melt is dynamic, and we're probably catching it in the act rather than, this is a permanent feature of the Lithosphere-Asthenosphere system. And then again, we have a relatively simple age progression in some places, but then we have things like drips telling us that maybe the evolution of the lithosphere, the tectonic plate, is a bit more complicated. So small scale convection at the base of the mid-ocean ridge plate is not a new idea. And in places like the Pacific, where you have really fast plate motions, these tend to organize and make nice gravity lineations and things like that. But the Atlantic is different, and it could be because of the slower spreading rates, it doesn't organize the small scale convection quite as much. So you have more like a lava lamp type convection that kind of drips things off, and you have active upwelling where melt coalesces and comes up to the surface. So this is kind of our cartoon, which I think I put with the abstract. But basically, the take-home message is that, well, it's a much more dynamic system that we think. And if we go into our imaging studies thinking that we're going to get the static picture and get the answer, well, actually, it's going to depend on the time and place, and that you have to, accept that the Earth is a lot more complicated than we thought it was, right? It's not just half space cooling. Okay, so just to take a few minutes to go global with this. So going back to our receiver function gather here as a function of plate age, there's a lot of scatter in this, and some of that scatter might actually be explained by this kind of undulatory lithosphere-asthenosphere boundary structure, right? And so, you know, you may look at this and say there's a wide variety of temperatures, but actually it may just be complexity in the base of the lithosphere. And then this is, again, just to kind of illustrate. So what we did here was we picked out the different melt geometries that different studies have put forward over the years and just kind of compared them at different ages. And you can see, you know, there's channels in some places, broad melt triangles and things like that. And seeing almost all those features in our one study area can suggest that, well, maybe all of those studies are right and what they're seeing is robust. It's just they're seeing melt in different stages of coalescing, et cetera. And so just to give you a plausible physical model as opposed to hand waving, saying that melt moves through the asthenosphere, this is some nice work by Joyce Sim, looking at two-phase flow, and the arrow down here is saying increasing half spreading rate. So at slow spreading, you have very complex porosity wave structure. So you have bits of, you know, as the solid compacts and decompacts, you have these kind of waves or bands of melt that move through the system. Whereas once you get to faster spreading rates, the melt migration is a lot more steady state. And so some of what we're seeing may be due to that. And then just to convince you that we can resolve these differences, so we've just taken one of these models and plotted it up. And you know, as discussed earlier, the surface waves will just average it out and give you a not very flattering picture of what it should look like. If you have high frequency receiver functions, you can resolve the top and bottom of it. But if you have low frequency receiver functions, you're going to have something that just looks like an LAB. Right? Okay. We've done some synthetic. And it's not just mid-ocean ridges and kind of mid-career ocean plates. It's also seen at the destruction of oceanic lithosphere. So people have argued that there is melt beneath plates. The Stern et al. Paper is a really beautiful example where they actually image the melt channel with active sources, which, you know, the ability to resolve things on sub-kilometer scale is always reassuring. But lots of other studies have inferred this. So it seems to be a pervasive feature. So if it's a pervasive feature beneath oceanic lithosphere, well, maybe it's a pervasive feature underneath continental lithosphere as well, right? And so this is just to remind me of the regionalization of the Earth, and these are just showing cratons in different places. And then this is, you can, you know, surface wave dispersion maps also kind of highlight, this is just clustering analysis, but basically highlight the same features. So continental lithosphere seismically looks very distinct from oceanic lithosphere. But a common refrain from people who study the continents, continents are thick, they're 300 kilometers. Well, actually, they're not that thick. If you look at the majority of the data, they're where you would pick the base of the lithosphere-asthenosphere boundary is kind of in the 200, 150 kilometer depth range. And actually, there's only a small fraction of the lithosphere that's 300, 250 to 300 kilometers. In fact, it's only 6 to 14%. So that's a tiny little bit. And that gets you to start thinking about, well, okay, if you have these tiny little bits that are that thick, do we have, this is a picture where everywhere, 300 kilometers thick, right? Very smooth, very easy to look at. But actually, maybe you have something that's a lot more complicated. And you have things that maybe dripping off or doing more complicated flows. And so maybe as unsatisfying as that is to some people, to look at that and say, well, this is the picture. This is actually what our oceanic lithosphere looks like. And this is actually what our continental lithosphere looks like with, maybe deeper dripping off things. We don't know. We have billions of years to wait to see if it actually drips off. And we have to maybe rethink how we're modeling and trying to understand the lithosphere-asthenosphere system in light of a lot more interesting observation. And I'll leave it at that.
For this fascinating talk. We're welcome to any questions if anyone has.
It's great talk, Nick. I had a question about the constraints that you have. You haven't really talked about gravity. Mm-hmm. Specifically, I was thinking about the downdrip. Is there a gravity expression to those kind of features?
We haven't looked in great detail. It's a good question. It's one of these on the to-do list. So I can say that, you know, unlike the Pacific, the Atlantic doesn't really have like those nice gravity lineations in them. Yeah, yeah. So that, and that, you know, nobody ever talks about the Atlantic because they're just not there. I do have to look into the whether or not there's a gravity expression. The other issue with that is that the density contrasts are probably still relatively small, and the surface expression, which probably would be the kind of smoking gun, may not be that large because it's thick plate already, so it may not, you know, be bending that much to give you a signal. But that would be my like hand wavy, but I have to go and do it to see if there is something. So.
You speak about these channels, layered mail at the base of the lithosphere, and the thing that comes to my mind immediately is yeah, so you will, you know, since you put melt at these kind of depths, you know, it's 20, 30 kilometers, it's like plagioclase kind of area, you will start to have very weak kind of, you know, channels basically, and they would be able to accommodate a lot of deformation. Did you see any features that could be linked to this kind of, you know, deformation, or is there any?
That's a good question, and that's, I guess that's one of these like if there's internal stresses that are built up because some parts are maybe sliding a bit easier relative to other places. Yeah, that would be a neat. I don't know if you'd be able to see it geodetically or with earthquakes or something like that. Yeah. There are a fair number of intraplate earthquakes, yeah, which I haven't discussed in a lot of detail, but in some of the locations of the drips, we do actually have little clusters of intraplate earthquakes. So not actually by the big drip. There's our postdoc finally published the local seismicity. Where is it? Okay, go back. The map, sorry. Good map. Okay, yeah. So you can see, even this is from the global seismic network locations, but you can see there's this little cluster of seismicity, interplate seismicity. It's actually fairly far away from the fracture zone, but there is, it's not the big drip, but there is a small, it looks like a developing drip. But again, this is like on the edge of overinterpretation, but there is actually a slight seismic anomaly there.
What I meant also, they could play a decoupling kind of role,
yeah,
for these drips, you know, so you wouldn't, like Harm was mentioning, you wouldn't see anything because it was decoupled from the rest of the upper part of the lithosphere.
Right.
So you would have like kind of this decoupled system drips of welling through these channels.
Right.
So you'd be very, and there's I mean, I've been looking at that quite a lot in the mantle or near the LAB, you know, there's quite a few places in continents or oceans, you have earthquake clusters, low, you know, very small, but many earthquakes that may be linked to this type of deformation. You know?
Yeah, it's a good question. Yeah, we know about those clusters of intraplate earthquakes. We just have to find a person to study them in a bit more detail. So we have focal mechanisms for a couple of them. They're relatively small, and that's one of these things that might be diagnostic of kind of the state of stress and what's causing it, if it's reactivation of some, you know, fracture zone stuff or not.
I'm sorry, just this the Southwest Indian Ridge. You know, I worked with Mathilde kind of on it. They see earthquakes in the mantle there, but the amount of melt is very small. So do you have any idea what kind of, it would be different from what you show? No, do you have some idea about very slow spreading ridges like that?
Well, that is one of these. It seems like every generation gets to do one ridge. So I think we already did our ridge, but the next generation, it would be awesome to go there or someplace like the Gackle to kind of understand, because that's it's so different, right? Yeah. I think seismically the Gackle, even though it's probably logistically more difficult, seismically it's probably quieter because it's sitting under ice. And I don't know how EM would do under ice, but
well, he did well, not in the Gackle, but Mohan's next to it. There's some good EM data out there.
Yeah.
Arm again.
So in your ideal fit between the magnetotelluric and seismic data, if you're discounting CO2, and only look at water content, you in your ideal reconciliation, you would have something like, I think, a 3% water content in those melt layers, while there's maybe only a 1% water content in mid-ocean ridge eruptions, if I understand correctly.
Yeah.
Is it then possible, if that has to coexist, that there's maybe a lateral gradient also in the melt content, that possibly near the mid-ocean ridges, that those melt channels maybe have a smaller melt content? Water content, I'm sorry.
Yeah, yeah. I mean,
it is kind of strange to have that such a large disparity.
right. Yeah. So, and this is a question that we're actively trying to reconcile. So, I mean, Satish, he's got some paper with Charlie Langmuir, and basically, you know, to justify their melt channels, they said it's got to be wet. There's no way, because otherwise they would freeze, right?
So it could be a very distinct off-axis feature, where off-axis it's possible maybe to have more water than when you're closer to the mid-ocean ridges.
Yeah, and so my geochemist friends always say, well, if you have a relatively, you know, if you have a melt triangle, you know, adding a small amount of melt with a large amount of water, it just gets diluted. So what you would see coming out of the ridge would be relatively low water contents, even if you were, you know, even if the channel was feeding some of that melt in. But it, you know, in the southern line there, they seem to be connected, but it's never clear like what the lateral transport is. Like Parmentier has all these models that say, well, it could be hundreds of kilometers, or, you know, it just gets sucked right up by the ridge, but it's not clear. But I mean, I think there's a lot of really neat modeling studies that could be done to see if you know, is there a separation zone? You have this melt channel, you have the mid-ocean ridge system, and, you know, is there, you know, a gap that forms or something like that eradicates the signal? But it's like one of these, the signal you don't see. So it's one of these odd arguments you have to make. Well, we don't see it, but we think it's there. So, but yeah.
Thanks. So is there like a critical age where you form these drips? Like, so basically, like, what forms the drips and like why they form in these places and like just drop off?
Yeah, so that's a good question. So let's go back to one of these that has a drip. Yeah, I usually put the age on that. So in this case, it looks like the drip is kind of forming between 30 and 40 million years. But it depends on how you define a drip. So there's like this little guy here that could, it's like, but over-interpreting, like, I'm gonna throw my hands up and say, no, I don't want to over-interpret, but there are places that look like maybe, but, you know, the whole system is moving. The interesting thing about getting drips and upwelling, mostly drips at relatively young ages, is that it suggests that there has to be a very low viscosity in the asthenosphere. So typically, to get small scale convection, to get those drips to develop, you have to have, you know, if you want to get it to develop at young seafloor ages, you have to have, you know, 10 to the 18 Pascal seconds or something like that, which is pretty low. So you could also flip it on its head and ask the question, well, you know, what viscosity, you know, placing a constraint on the viscosity of the mantle by saying, well, we see this drip and this is the viscosity range that's acceptable in the mantle, and then trying to also incorporate, you know, the effect of melt on that. So again, more games you could play and fun that you could play around with. So
okay, thanks.
Good question.
Kind of piggybacking off that, in like looking at these drips and everything, and especially like geodynamically, you're in between two fracture zones. Have you thought about doing some sort of like numerical modeling project that can incorporate melt to kind of look at this more in a lateral extent? Yeah,
so that is also a good question. So the fracture zone may also be an important part of the story because of kind of edge-driven convection kind of considerations, and that is something we've thought about. But again, my numerical modeling skills are relatively weak compared to some of my colleagues. So I can do small things, but you know, I have to call in the professionals to do like the fancy three-dimensional things. But you know, I'm always happy to talk about it. I'm giving the geodynamicists plenty to work on here, which is exciting, right?
Yeah, it's really, really cool. Thanks.
Yeah. Excellent.
We have a question on Zoom from our colleague Dallas. You can unmute and ask your question, Dallas.
Thanks, Eric. Yeah, thanks for a great talk,
Yeah.
Nick. It was very interesting. I particularly enjoyed the use of MT to resolve the seismic data. It's kind of the opposite of what usually happens. So that was
Dallas, we actually can't hear you in the room. Do you mind? Sorry about this. Do you mind popping your note in the chat, and then I'll ask it. For some reason, we just can't hear you.
I'm just gonna ask Achille to get Dallas question. I was wondering, just from the pragmatic perspective of you, now that you know it's more complex and going model, how would you design this server or a different reach? You've done your reach, but some other people who would do a different reach, better way. It's like longer deployments, more instruments, pressure gauge. What would be the ideal? Your next
As a seismologist, it's always more instruments, wider aperture, wider spacing. Yeah. I mean, from a practical perspective, I think ability certainly to do, our deployment was relatively small, and that was kind of limited by the funds we could raise, and the fact that we had to do it through, we basically had to rent the equipment, whereas like in US pools or German pools, the avail 80 instruments is possible, right? So double our experiment. Logistically, the amount of ship time you need to deal with 80 instruments is, potentially daunting. But no, I think people could definitely do bigger and better experiments these days, for sure.
I've got Dallas's question now. Is that on? Let me see if this is on. All right. So you can't hear me. Do you hold it down, or do you just?
Yeah, exactly.
You just talk, and now it's still not working. I'm just going to yell it out, and then can you repeat it?
Yeah.
Dallas asked whether you attempted to include an anisotropy in the MT inversions as well, and if there are vertical oriented melt channels, I would expect that to show up in the resistivity as well.
So the question is, was anisotropy included in the resistivity inversions, and whether or not vertical, if anisotropy was included, did we see evidence for vertical melts? I think we played around with anisotropy, but I don't think we got very far with it. And I think Shengguo had to do a few tricks to get the inversion to work, which I think limited the number of well, Eric can probably speak more to this, but limited the number of actual observations that you could use to pull out information about anisotropy. But there are bigger effects, like coastal effects, that we have to probably deal with before we start diving into that or figuring out. But it would be cool to see that, because it's a good idea to look for that, because that would really support the seismic anisotropy. So that's a great idea. I'm going to go run off and write it in my notebook and try and write a Science or Nature paper about it.
Just a quick note about that as well. This is kind of a half-hour FT version because of the coastal effect, although the very powerful Africa, there was still significant coastal effect that the normal MT2D version was not really capable of overcoming. So it's kind of determined the inversion, which is half-hour in a way. It's kind of a work around it. But once if we do have like better capabilities in 3D modeling, then probably those constraints will be in effect. Yes.
Going to the version 6 cannot should be inversion, like the inversion considered also like ATD cannot.
Yeah, using carry keys, MAR 2DM or whatever, but just modified.
Yeah, but those are still kind of growing capabilities in the public availability.
Yeah, and to be fair, I mean, the mid-Atlantic is a 3D problem, you know, even just with the geometry we have. So, you know, we're kind of taking a step back and saying, okay, well, you know, the 100 kilometers of ridge segment that we have is good enough for the kind of 2.5D approximation, but, you know, it'd be cool to go across the fracture zone too.
Good. I think we're on time.
Thanks.
Any other questions?